We know from our study of differentiation that anytime we have a function, let's call it f of x, that could be thought of as being the sum or difference of two other functions. So that is to say, if we had f of x equal to g of x plus or minus h of x, then we know that we can get the derivative, f dash of x, as the derivative of those two parts. Now we see this all the time if we're asked to find the derivative of 2x squared minus 3x to the 6. All we have to do is differentiate the first component, differentiate the second component, and we subtract one from the other. Now, I don't think you need me to go through that, but you can see it just over here. So the question becomes, well, what happens if things aren't just separated by a plus or a minus? Now, the first, I suppose, way in which we've approached this and had a look at this is whenever we've had a look at the chain rule. So in this case, we consider a composite function. Suppose we had f of x, where f of x is equal to g of h of x. And so we may just think of the fact that within this g is an h. Now, in order to do that, we treat the g of h of x as though it was g of u, or any variable really. And we take the derivative of the inside, h dash of x here, and we multiply by the derivative of the whole thing. Now, in general, what we might say is, suppose that y equals f of u, where u is some function of x. Then we know that dy dx, the derivative of that with respect to x, is going to be the derivative of what's inside, u dash of x, times the derivative with respect to u. And finally, at the end there, we'd need to resubstitute. So we'll do an example of this in a moment. So an example of the chain rule here is we're being asked to find the derivative of f of x, given that f of x is sine 2x squared minus 3x to the 6. So we can imagine our nesting function here, our h of x, or our u, being 2x squared minus 3x to the 6. So we do this with a simple substitution. Let's let u of x be equal to 2x squared minus 3x to the 6, so that we know f of u is equal to sine u. Now we can differentiate each of these. We know that u dash of x, the derivative of u, is equal to 4x minus 18x to the 5. We know that f dash of u is equal to cos u, being the derivative of sine u. Now the chain rule, we can consider this as being f dash of u times u dash of x. So we take these two things here, we multiply them together, and if we want to give a little bit of context here, f dash of x, what we were asked to find, is equal to, well, f dash of u, which is cos u, or really, it's going to be cos 2x squared minus 3x to the 6 times u dash of x, which is 4x minus 18x to the 5. Now we've done this a few times, and we should know the chain rule a fair bit by now. In fact, we learnt the sine of a function. The derivative of that would be the derivative of the function times sine of itself. So we've covered this in some detail. What's new for us is the product rule here. Now suppose we have one function which can't be represented as a nesting function, but instead is something times something else. So suppose that our function f of x here was one function, let's call it g of x, times another function, h of x. Well, we know the derivative of f is going to be the derivative of the first function times the second function itself, so g dash times h, and we add that to h dash times g. Now, using functional notation, this can get a little bit tricky, so we normally remember this as saying, suppose y equals u times v. Well, dy dx, the derivative, is equal to u dash v plus v dash u. The derivative of the first times the second function itself plus the derivative of the second times the first function itself. So putting that into context, if we're asked to find the derivative of f of x, which is x squared log e 2x squared, we can first think of this as saying, well, let's let u equal x squared, and let's let v equal log e 2x squared. Well, if we now derive both these things, u dash is equal to 2x, and v dash, well, the derivative of log of a function is going to be the derivative of what's inside, so we get 4x divided by what's inside itself, which is 2x squared. We note that the x's cancel down once, and that we end up with 2 over x. So if I've got u equals x squared, u dash equals 2x, v equals the natural log of 2x squared, and v dash equals 2 over x. There are 4 pieces. We know the formula is that f dash of x will be u dash v plus v dash u. So my u dash is 2x, let's get that over here, times my v, so 2x log e 2x squared, plus my v dash u. So I need to add my v dash, which is 2 over x, times my u, which is x squared. And if we think 2 over x times x squared, well, one of those x's will cancel, and we get 2x log e 2x squared plus 2x. Last step here would be to simplify. If we take out our common factor of 2x, then we end up with the natural log of 2x squared plus 1. And if we want to contextualize this, we know we're asked to find f dash of x. That's it. Another example we have here, find the derivative of f of x, where f of x equals e to the negative x tan 2x. Well, my first function, e to the negative x, let's call that u. And let's call the second function, tan 2x, v. Now, the derivative of u, let's call it u dash, that's going to be negative e to the negative x. Now, I find that by deriving the top bit there, negative 1, and bringing it down to the bottom. For my derivative of tan 2x, my v dash, well, the derivative of 2x is 2, and the derivative of tan 2x is sec squared 2x. And so we find the derivative of tan 2x to be 2 sec squared 2x. Remember that the secant function there, or sec, is just 1 over cos squared. Now our formula is going to be u dash v plus v dash u. So if we think u dash v, well, negative e to the negative x times tan 2x plus my v dash u, so that's going to be, if I write this out appropriately, 2 e to the negative x, sec squared 2x. Now looking at this, the only simplification we need to do is to take out, let's perhaps think e to the negative x as a common factor. Which would leave minus tan 2x plus 2 sec squared 2x, which I might rewrite as 2 sec squared 2x minus tan 2x. Just to ensure that our notation is consistent, f dash of x there. Beyond taking out a common factor, we'd rarely need to do anything more than simplify. But if we think about what our, base strategy would be here, the first thing that I did, was label u and v. The next thing that we did was to think, let's find u dash and v dash. So find the derivative of these pieces. We sub that into our formula. Which is on the back of the formula sheet. Doesn't need to be memorised, but an easy way to remember that would be just u dash v plus v dash u. And we finally simplify, take out any common factors. So we'll see if we can use this same strategy for our next example. We're being asked to find f of x, where f of x is equal to one function, x cubed, times the second function, 10x squared minus 5, all cubed. The way that this differs from the previous example is that we actually have to use a chain rule in order to find the derivative of the second. So although it's a product rule question, the chain rule is kind of nesting within it. So our first function u, let's just undo that, my apologies. First function u is equal to x cubed. Our second function, v, is equal to 10x squared minus 5 cubed. Now the derivative of u, we'll call it u dash, is a simple one, just 3x squared. But the derivative of v is a little bit harder to work out. So we can use the shortcut for the chain rule here. If we drop the 3 down, we get 3 times the derivative inside here. Now the derivative of 10x squared is 20x. And we're going to multiply that by the bracket 10x squared minus 5 minus 1. So that's all squared. So v dash is actually 60x times 10x squared minus 5 squared. Now if we go to our formula, we know that for the product rule, we're after u dash v plus v dash u. Well, u dash is 3x squared times v there. So we've got 3x squared outside of 10x squared minus 5 cubed. Now we're going to add my v dash times u. So 60x times x cubed is going to be 60x to the 4 times 10x squared minus 5 squared. Now a lot of people would leave their answer here, and it's somewhat difficult to realise that we actually have a common factor, not only of 10x squared minus 5 all squared, as that goes into this cubed here, but also we have a common factor of 3x squared, which goes into 60x to the 4. So let's start by removing the 3x squared which goes directly into that, but of course leaves 20, so 60 divided by 3, x squared here. And if we take out 10x squared minus 5, squared, well, 10x squared minus 5 cubed divided by 10x squared minus 5 squared leaves a bracket of 10x squared minus 5. And if we take it out of here, they just cancel, and so we just get that plus. So it looks a little bit complicated, but we're about to clear it out. Give ourselves a little bit more room here. So we've got our common factor of 3x squared, 10x squared minus 5 squared. If we think about this, we don't really need these brackets here. And 10x squared plus 20x squared is going to be 30x squared minus 5. That's as simple as it gets. So we'll recontextualize our answer, f dash of x.